Okay, so I want to welcome everybody to the Western Hemisphere Colloquium on Geometry and Physics. Just a few quick things before we start. Everyone will remain muted during the lecture, but we do encourage questions, which you can submit with the chat feature. You can chat the question to everybody. And after the lecture, there will be a Q&A where you should use the raise hand feature in the participants panel. So without further ado, this week's speaker is Ben Webster from the University of Waterloo and the Perimeter Institute, and his title is 3D Mirror Symmetry and its Discontents.
All right, thanks so much everybody for coming, and of course thanks to the organizers for the chance to speak. So, that wasn't what I meant to do. Here we go. So, quantum field theory. It's a subject that I've certainly struggled with a lot over the years, and I suspect the same is true for many of you. I encountered this image on the cover of the Quantum Fields and Strings course a long time ago, and now I've started like using it at the beginning of all of my talks because it's like, welcome to my life. This is me standing down in the bottom right corner here. So I had never thought that I was going to do quantum field theory. I really thought I was a geometric representation theorist, at least when I started my career. And then somehow I was lured into the woods of quantum field theory. And so I'm here to sort of try to impart whatever knowledge I've gained by doing that to all of you. So it's a slightly easier trip. So let me just give you some very, very basic context. What I was interested in is I was interested in understanding the representation theory of non-commutative algebras, which aren't too non-commutative. They're commutative enough that they have semi-classical limits. So the classic example of this, you take the universal enveloping algebra of a semi-simple E algebra. It is semi-simple for reasons later. And that has a semi-classical limit. So the PBW theorem tells you that that's a quantization of functions on the dual of the Lie algebra, and that the sort of first order part of commutator is this well-known Poisson structure on G star called the constant Kirillov-Surya bracket. So if you're used to the statement that coadjoint orbits are symplectic, well, all of those symplectic forms on the coadjoint orbits actually fit together into a Poisson structure. So it's sort of, I don't know, I prefer to think of it as kind of one big structure in all of G star rather than symplectic forms on the individual orbits. So this space, I'm just giving you very basic context. Like there's some talks I give where this part takes like 30 minutes to explain. This is a very nice space. It's the universal deformation of a space that's, well, pretty close to symplectic, except it's singular, the nilpotent cone. So I kind of prefer to think about the nilpotent cone rather than G star. And my explanation is, G star you can actually get by taking the nilpotent cone, looking all the ways of deforming it while keeping its Poisson structure. And there's another interesting object in there, the Springer resolution. So this is a resolution of singularities of the nilpotent cone by the cotangent bundle of the flag variety. And the cotangent bundle of the flag variety is, of course, symplectic, and this map is compatible with the Poisson structures. So there's this sort of beautiful system here of there's an algebra, the universal enveloping algebra, there's its classical limit, there are these sort of games you can play in algebraic geometry, there's this resolution, there's this deformation, sort of all of these things play together and make a really nice mathematical package. And there are several other instances of these where you have an interesting non-commutative algebra, you have a symplectic singularity, and you have a similar kind of story, though almost all of those are less well investigated than this one coming from semi-simple Lie algebras. So that was the kind of thing I thought I was studying. Sounds like a very mathematical thing. And I mean, of course, there's Poisson structures, like you could see how there might be some physics involved, but it doesn't seem like something where obviously quantum field theory is the right way to think about it. But it turns out that quantum field theory maybe is the right way to think about these things. So the sorts of objects I was talking about, a non-commutative algebra, its semi-classical limit, deformations, resolutions, all of these show up naturally in three-dimensional quantum field theory with n equals 4 supersymmetry. And I'll do my best, right? One of these things that I didn't know for a very long time, and it's still debatable to what degree I know it, but I know a little bit more, is why is it n equals 4? So maybe I'll explain them, sort of reasonably well why it's 3 dimensions, but why is it n equals 4? Well, at least part of why it's n equals 4 is that's a lot of supersymmetry to have, right? 4 is bigger than 1 and even bigger than 2. And if you have n equals 4 supersymmetry, you're guaranteed to have some topological twists in your field theory, which is a good thing to have. It sort of tells you that there are interesting bits of your quantum field theory which are purely topological. So for each one of those topological twists, there's this natural structure that shows up. The local operators of that twisted theory, so I use a odd element of the supersymmetry algebra to give myself a differential on my space of fields, and I take cohomology with respect to that. That's topological twisting. I get some local operators in that twisted theory, and those carry a Poisson bracket. So they have a multiplication coming from points colliding with each other. But those points can collide in a bunch of different directions. And because it's 3-dimensional, there's an S2 of directions where they can collide. And so there's a secondary product that comes from integrating over that S2 of directions they can collide from, which gives me a Poisson bracket. So if I'd been 2-dimensional, I would get a super Poisson bracket. I would get something that was algebraically very different. So the 3 actually is important because that's what gives me a Poisson bracket of degree -2. And furthermore, I can turn on what's called an omega background, which just means looking at the U1 rotating R3. So maybe I'll actually try to do a drawing, right? I have my R3 here, and then I look at the U1 that rotates around one of these axes. And working equivariantly with respect to that is, in physics lingo, turning on an omega background. Instead of having a topological twist, you take a twist that squares to the generator of that rotation. And that sort of incorporates that rotation into your picture. Okay, so in fact, I said, okay, there are these things I'm interested in: symplectic singularities, non-commutative algebras attached to them, symplectic resolutions. Well, it turns out there's a natural source of these 3-dimensional field theories with n equals 4 supersymmetry. And all the examples that I cared about, that I thought were cool, actually come from 3D field theories. So this is how I ended up accidentally interested in 3D field theories without intending it at all. Now, another thing that n equals 4 gives you is that there's not just one topological twist. There are 2 particularly important ones, and I'll call these A and B, and throughout, I'm going to use red for things related to A and blue for things related to B, because otherwise I will get confused. Now, I'm not going to get into the algebra of the supersymmetry algebra here, but one thing that I find it very helpful to think about is, because it's n equals 4, there's an R-symmetry action of spin 4. And spin 4 is SU2 times SU2. And somehow there's a red copy of SU2 and a blue copy of SU2. And like everything in this picture comes out of that. So yes, it's also worth mentioning, you might be used to having twists called A and B, but you're used to those showing up in 2-dimensional theories. And it turns out that that's not a coincidence. These names are the same for a good reason, because there's a particular way of putting 2D n equals 2, 2 theories on the boundary of a 3D theory that makes these twists match up. So your spidey sense should be going off that I'm telling you, oh, there's some relationship to 2-dimensional mirror symmetry, which is the mirror symmetry that mathematicians and also most physicists are most familiar with. And again, it's sort of the easiest manifestation of this to see is in the R symmetry, that what's happening is in that 2, 2 theory, there's a red copy of 2 and a blue copy of 2 that give you the A and B twists in the 2D theory. And we have an inclusion of our symmetry of U1 cross U1. The red U1 goes into the red copy of SU2, and the blue U1 goes into the blue copy of SU2. So 2D mirror symmetry is basically the idea that Kähler manifolds, obviously there are lots of ways of weakening, putting Kähler there, but let me just say Kähler to make my life easier, should come in pairs such that when I look at the 2D sigma models, if I swap the role of the A and B twists, I'll swap from one manifold to another, right? So that for out of a Kähler manifold, I always get a sigma model, which is a 2-dimensional 2, 2 theory. And that if I swap the role of the 2 2s or swap the colors, I'll get the sigma model attached to a different manifold, which is its mirror. And for example, homological mirror symmetry, which is the version of this that I like best, is just the statement that categories of boundary conditions compatible with those 2 twists should interchange. All right, well, obviously the D equals 2 case is very rich. I'm not going to try to say anything about it because I don't have much in the way of special expertise there, but you can do the same thing in 2 dimensions. So you can ask, well, are there pairs of 3D n equals 4 theories which differ only by swapping the roles of the A and B twists? Maybe there are, maybe there aren't. And in fact, I just wanted to put this up because, again, this is one of these things that nobody explained to me for a long time, and I think is actually really kind of important to know, that in 1, 2, and 3 dimensions, right? So if you have a 2-dimensional theory, it might sit on the boundary of a 3-dimensional one. If you have a 3-dimensional theory, it might sit on the boundary of a 4-dimensional one. And in each of these dimensions, there's a notion of taking dual, which is compatible with this considering theories on the boundaries, which in 2D is the sort of usual mirror symmetry, in particular, its homological version due to Kontsevich. In 4D, so this is, I'll just call this 2D mirror symmetry, it often manifests as T-duality. I was told by tutor that I should be careful to not call this T-duality because T-duality is only one manifestation of it. So that's why T-duality is in parentheses. And then there's also a very famous duality in 4D, which corresponds to geometric Langlands. This is electric magnetic duality, or also called S-duality, which was connected to geometric Langlands by work of Kapustin and Witten. And it turns out that in between those is 3D mirror symmetry, which can sit on the boundary of the 4-dimensional guy or carry the 2-dimensional story on its boundary. And this, well, some collaborators of mine gave this the name symplectic duality because it involved these symplectic manifolds. I kind of never really warmed to that name, but if you just forget about the implectic part, it becomes S-duality, and well, that's what it's called in physics as well. All right. So an obvious question for mathematicians is, well, how does this duality of theories manifest? I mean, we've just got an incredibly rich amount of mathematics coming out of 2D mirror symmetry. So what's the mathematics that comes out of 3D mirror symmetry? What are the interesting things we can learn as mathematicians? And I'll just say, we know a lot of interesting examples, and I'll try to talk about those a little bit later. I only have so much time in my talk. And a lot of interesting hints about what's going on. I would say, the full picture is still not in focus. We don't really understand. I think if you come back in 10 years, I'll be able to give you a more satisfying answer, but we're making progress and we're a lot closer than we were before, thanks to recent work of a lot of different authors. So maybe I'll pause here for questions. You can see I'm at the end of one of my sections.
There were questions, but I think they've been answered. So
okay, great. Probably many questions that would come up during that discussion. There are people in the audience who are more qualified to answer than I am anyways. Okay, so just to remind you why I'm so interested in 3D theories, their ring of local operators, once you put in this topological twist, has some nice structures. It has a commutative algebra structure coming from colliding operators, has a Poisson bracket coming from integrating over all the different ways things can collide, and it has a grading that has to do with this twist. So if I think about spec of that ring, I have a commutative algebra. I'm a mathematician. I immediately say, oh, commutative algebra, that's a ring of functions on a variety. I would rather look at a variety than an algebra. So I can get an affine algebraic variety. It's going to have a Poisson structure because of that Poisson bracket on functions. And it's going to have a C star action or a GM action more generally that scales the Poisson bracket, because the grading, the Poisson bracket had degree -2 with respect to the grading. And I'll say, these are all structures that come up if you have a hyperkähler manifold. Physicists always tell me, no, there really should be a hyperkähler metric on this thing. I don't know any mathematical way of justifying that, but it does seem to usually work out that there's a hyperkähler metric. And you'll recall you should get 2 of these for each theory because they're A and B twists, and you'll usually hear these called the Coulomb branch and the Higgs branch. And again, keeping with my convention, Coulomb is red and Higgs is blue to remind you which twist they come from. So the best understood of these 3D theories, and I immediately am going to forget about all other ones, are the gauge theories, which come from taking a compact connected Lie group and a complex representation of that Lie group. And in physics terms, we take the hypermultiplet for the representation V, and we couple that to the vector multiplet for the group G. So the Higgs branch of that is the hyperkähler quotient. And in fact, this is one of these things I have been told, and I regard it as too good of a story to check, that essentially hyperkähler quotients were discovered because they were the Higgs branches of these theories. The Coulomb branch was much more mysterious. So when I first came into this field a bit over 10 years ago, people told me, well, yeah, there's this Coulomb branch. It's kind of close to being, take the cotangent bundle of the dual torus of your gauge group and mod out by the Weil group. But that's not quite right. So they say, you know, that's kind of the right idea, but that's not actually the right answer. There are some quantum corrections. That's the classical version of the Coulomb branch, but there are quantum corrections. The hyperkähler metric changes. This somehow forces the topology to change. And I couldn't get a clear explanation of what was going on. So part of why I didn't get very far in understanding things in terms of quantum field theory was, for a long time, the physicists couldn't tell me how these Coulomb branches worked. Now, luckily, Braverman, Finkelberg, and Nakajima have given a sort of precise description of this ring that tells you algebraically how to compute these quantum corrections. So I will get to that later in at least a little bit more detail, but the important thing to know is sort of a complicated geometric description involving the affine Grassmannian, but it also has an algebraic presentation. And as I say, 3D mirror symmetry swaps the A and the B twists, so it swaps the Higgs and Coulomb branches. And in fact, most of the precise calculations of Coulomb branches that were known 10 years ago came from finding some other justification of the fact that theories would be mirrors of each other using string theory and computing the Higgs branch of the other theory and saying, ah, that must be the Coulomb branch. That looks roughly correct. It sort of follows this prescription as do this quotient by the Weil group and then make some modifications. So that must be the right answer. So what are some examples of these? So if I take n plus one dimensional space and let u1 act on it by just the obvious scalar multiplication on every coordinate, then the Higgs branch will be the hyperkähler quotient, T star Pn, or its affinization, which is n by n matrices of rank no more than 1. And the Coulomb branch will be C2 mod this cyclic group of order n plus 1. And I'll just mention here, right, there's no Weil group here. So the classical prescription told me that this should be the cotangent bundle of C star. The kind of classical Coulomb branch in this case would be T star C star, which is definitely not the same as C2 mod the cyclic group. So somehow classically, we couldn't see any difference between these guys. The only change is in the quantum corrections. On the other hand, if I take u1 to the n and let that act on Cn plus 1 as the unitary diagonal matrices with determinant 1, so that's kind of the complementary thing to acting by the same scalar on all the coordinates, well, the Higgs branch is then going to be this quotient of C2 by the cyclic group of order n. You'll note here I'm not being totally consistent about whether I'm writing down an affine variety or its resolution. T star Pn is a bit better known than the n by n matrices with rank no more than 1. This guy C2 has a natural symplectic and in fact a unique symplectic resolution. So I could have written that instead by just putting a tilde here. And the Coulomb branch is T star Pn. And again, if I had just taken the classical Coulomb branch, I would have just seen T star of C star to the n. So it's not, this classical Coulomb branch wasn't seeing a lot of interesting stuff going on. I always get the same answer for an abelian gauge group. And in general, it's totally insensitive to the representation V, which is called the matter. All right, and then there's some more interesting ones like, whoa, hello? Okay.
Go ahead.
All right. So if I take the GLN with the adjoint representation plus the vector representation, I get the nth symmetric power of C2, which is resolved by the Hilbert scheme. So you should also think about Hilburn of C2 here. And that shows up as both the Higgs and the Coulomb branch in this case. And this one is a little bit more complicated. I tried to write this out in terms of representations, but it's maybe better to write the quiver. So this is the quiver gauge theory attached to 1, 2, 3, 4, down to, no, did the wrong thing there. I want n minus 1 and then n in a square node. So that means I take a map from here to here, from here to here, from here to here, from here to here, and that's these factors of matrices. And then I let the GLs of these spaces, GLN minus 1 here, et cetera, GLN minus 2 here, act by pre and post composition. All right, and that gives me the nilpotent cone in SLN. Again, both as the Higgs and the Coulomb. And then there's some more interesting theories where you can get the Toda phase space or slices in the affine Grassmannian. But maybe since I won't be getting into those in great detail, I'll leave those for later discussion. Now note here that if I look at these first two examples, the Higgs of one is the same as the Coulomb of the other, and vice versa. So 1 and 2 are a dual pair. They're related under 3D mirror symmetry. And similarly, 3 and 4 are each self-dual. And again, this sort of manifests in seeing that their Higgs and Coulomb branches are the same. And both of those can also be justified in terms of this string theory. So that's not the only piece of evidence, but that's kind of the easy way to see it. So cases I particularly like are when my group G is commutative, in which case this Higgs branch is what's called a hypertoric variety, or a toric hyperkähler variety. And V comma G, and the other case I particularly like is V comma G being one of these quiver gauge theories corresponding to a linear or cyclic quiver corresponding to a dominant weight. And in that case, the Higgs branch is a Nakajima quiver variety. So if you like Nakajima quiver varieties, you should think, okay, the representation and group I have to put in to get these Nakajima quiver varieties. And one reason I like these cases is these are ones where the dual of a gauge theory is again a gauge theory, and it's in fact of the same type, but related by some combinatorial change of data. So for the hypertoric variety, there's a notion of Gale duality for torus actions on affine spaces, and you apply that and get another torus action. So here, these two actions of U1 by all the same scalar and by the determinant one matrices are Gale dual to each other. And it's a taking perp type operation. So you can see that those guys are perps of each other, and there's a generalization to that. And for these quivers, it's a much more complicated operation, but still very nice combinatorially. It's what's called rank level duality. So I definitely don't want to get into the combinatorics of that, but it is something that's purely combinatorial. So how did I end up here? How did I end up giving this talk? As I say, it was kind of a little bit of an accident. I was interested in non-commutative algebras, and you can get those out of these 3D theories. So I've been talking about Poisson algebras, but you can turn on an omega background or a twisted omega background if you want the B twist to get non-commutative algebras, which are star product deformations of these Poisson structures. And I and some collaborators, Tom Braden, Tony Licata, and Nick Proudfoot, had noticed there were some interesting cases where these two representations, these two algebras, I mean, the representation theories are very different, but there was sort of a piece of it called a category O that were almost the same. So they were related by what's called Koszul duality. So they're derived equivalent, but in a particular interesting way that swaps simples and projectives. Now there's a proof of this in general for gauge theories with a few caveats due to myself in the last few years that depends on this BFN description of the Coulomb branch and thinking about the category of line operators compatible with the A twist, but does some non-physical things in the middle, sort of uses the combinatorics of those and then goes off and does a little bit of math till we can find this equivalence. So the latter half of this talk is going to involve a lot of mysteries. So it's going to be me kind of advertising, hey, here are some weird mysteries. So here's one. We have this notion of 3D mirror symmetry for field theories. We've found in a bunch of interesting examples and in a reasonable level of generality that we get this Koszul duality between these pieces of the module category. What does that mean from a physics perspective? I'm not sure. And I should note, you actually get quite well-known non-commutative algebras out of this operation, as you might expect. So usually, if you can guess what the non-commutative algebra is, that will be right. So if you put in T star Pn, what do you expect? Differential operators on Pn. If you put in symmetric powers of C2, or more generally C2 mod cyclic groups, you'll get what's called a rational Cherednik algebra. And if you put in the nilpotent cone, of course, you get the universal enveloping algebra of SLN. And if you put in the affine Grassmannian slice, you get these interesting guys called shifted Yangians. I'm definitely not going to be able to get into those. So this is just pointing out these are not just weird random non-commutative algebras you've never heard of. They're quite interesting and natural ones. And there is a physical proposal for what we maybe should do, but this was kind of, it's toward the end of this rather long paper, Bullimore, Dimofte, Gaiotto, and Hilburn. And as far as I know, it hasn't been developed much since. So in this 3D picture, right, we've turned on our omega background. So we've incorporated this rotation. And one way of sort of dealing with that physically is to turn this plane into a cigar. So instead of a plane, we have this cigar shape, and then we squeeze the cigar down to nothing and end up with this two-dimensional picture. So we get a two-dimensional field theory, which we can make limit to sigma model into the Higgs branch or into the Coulomb branch. And you might notice there are these funny tildes here. That's because really you should be going into a resolution of the Coulomb branch or the Higgs branch. I'll talk a little bit more about those resolutions soon. So the proposal that Bullimore, Dimofte, Gaiotto, and Hilburn have is that these category O's can be interpreted as boundaries to a particular twist of the 2D theory. So it's not just the sigma model itself. You have to then do a further kind of limiting procedure of those. And ultimately what you should get out is an A model, which because of the real Fi and mass parameters, doesn't just give you the whole Fukaya category of the Higgs branch or the Coulomb branch. It gives you this category O, which is kind of a more constrained piece of the Fukaya category, or I should say A-branes. And the Koszul duality, we should be able to explain by saying that this category doesn't change as we move our twist through a path in the space of twists for this theory. That at one end, you'll have the A model on the Higgs branch, at the other end, you'll have the A model on the Coulomb branch, and then in the middle, you'll have some funny guy. So the picture they sort of have is, here's the Higgs, here's the Coulomb, and then there's some balanced guy in the middle, which I don't understand very well, where the category doesn't change along either of these paths, and that explains the Koszul duality. Oh, we'll have to see. Sort of in preparing for this talk, I got thinking about this stuff more again. I'm like, oh, I really should figure this out, but I haven't yet. All right, maybe I'll pause again to see if there are more questions.
No, I think you're good.
All right, great. So that was sort of one direction, the kind of earlier direction I had thought about. But in recent years, there's been another interesting development of trying to understand these theories, understand the duality around them, which is to think about line operators compatible with each twist. So these are a bit less obvious as mathematical objects, but they're very natural from the perspective of the physics. And mathematically, they're something one can get one's hands on. So one way to think about, to get a handle on what happens with these twists, is to think about the line operators you get from them. So this is, you know, if you go through this whole algebra geometric way of thinking about field theory, has to have to do with something about the space of maps from S1 into your target. And it turns out, if you sort of follow through what all these twists mean, if you do the A twist, you look at the space of maps from S1 into V mod G. So this is a gauge theory. It involves this representation and quotienting it by this group G. And then you should take the de Rham stack of that space. That's what this dr means. So, okay, that looks a little weird, but what that practically means, so this maps from S1 into here, that's the loop space of V mod G. You should be able to interpret that as Laurent polynomials in V mod Laurent polynomials in G. And then I take dr. What does that mean? Well, it means I take the D modules on that space instead of the quasi-coherent sheaves. So the de Rham stack, if it's not something you're familiar with, don't worry about it too much. It means you think of your the DG manifold where the functions on it are the de Rham complex. So this means that sort of in functions is sort of built in having a flat connection on everything. So in particular, if you follow that through, that tells you a coherent sheaf on this is a D module. On the other hand, if you take the B twist, well, it looks almost the same, but that de Rham stack sneaks into a different spot. That's the difference between the A and B twists. So this de Rham stack, it sneaks inside the mapping space, and I'm looking at maps from S1 de Rham into V mod G. So, I mean, that probably looks kind of horrible. It's not so bad. It's the space of principal G bundles with a connection and a choice of flat section of the associated V bundle, all of this happening on S1. If you just unpack what de Rham stacks mean, that's really what you're talking about. And the kind of interesting piece of this, shoot, that shouldn't be there. Thought I had fixed this, but maybe we're looking at the old version of the slides. Or maybe I just forgot to recompile my slides. We'll see. Sorry, so that shouldn't have been there. Just that has a piece which looks like the quasi-coherent sheaves on the cotangent bundle of the stack V mod G. So there's some other stuff in this category that's even weirder than thinking about that stack, but that stack's going to be enough for us. So one reason that this was a sort of profitable way of thinking about things is this is how Braverman, Finkelberg, and Nakajima figured out what the Coulomb branch was. So you can find the local operators of the theory inside this category of lines by looking at the trivial line. Excuse me. And that's actually sort of how you can do the computation of what the local operators are supposed to be. You compute the trivial line in the A twist. That's a D module on here, and it's the D module of functions on the Taylor series, mod the Taylor series in the group as a D module on this loop space. And then you can go back and read Ginsberg and Chris, and they'll tell you the right way to calculate the endomorphisms of that object is to look at the Borel-Moore homology of a fiber product. And that is Braverman, Finkelberg, and Nakajima's description of the Coulomb branch. Okay, so that's pretty profitable. We've learned like a lot of interesting stuff in recent years by using that description of the Coulomb branch, but there's a lot more going on. There's more in these categories other than the trivial line. And one way of saying that is we weren't talking about affine varieties there. We were talking about these weird stacks. So what else is in this category? So in the B-twist category, there are natural objects called Wilson operators or Wilson lines, you'll often hear people say. So these are just, when thinking about it as coherent sheaves, right? I was just saying coherent sheaves on here. That is the coherent sheaf, the vector bundles that come from G representations on any quotient by G. On the other hand, in the A-twist, there are these sort of natural objects called vortex operators. And these correspond to, you take some subgroup H inside the, these should all be parentheses. Sorry about that. I wrote square brackets, but I meant parentheses everywhere. So apologies. You take a subgroup in the gauge group, and you take a subspace inside the space of Laurent series in V, which is invariant under H, and you look at the push forward D module of the quotient. This is kind of a very natural geometric way to cook up D modules. And so, well, we have sometimes, at least in some cases, two dual gauge theories and two different kinds of line operators on the two different sides, but of course they have to match up, right? So CA for one theory has to be equivalent to CB for the other theory. I'm putting a prime here to tell you it's for the dual theory. And these are completely different looking categories. So it's kind of a natural question. How do things match up? Well, in the case of Geobelien, there's a really nice answer. I can tell you exactly what it is. It's not something I want to worry about right now, but it's very clean. But if G is non-abelian, life is much more complicated. So there's a nice work of Asel Gomez on cyclic quiver gauge theories, which I had emphasized as an interesting one. So the Wilson operators there do have a vortex description. They can sort of tell you what the D module on the loop space corresponding to the Wilson operators is, but it's not something of just this form U mod H. It involves a superpotential. It's considerably more complicated. On the other hand, there are coherent sheaves, objects in this line category we can cook up using a simple vortex description, which are provably not Wilson operators. So one example of this is you can get the Hilbert scheme of C2 that has a very special vector bundle called the Procesi bundle, which is very easy to cook up as a vortex line and provably impossible to construct as a Wilson line. So somehow, there's more going on in the story than just what you can see with the Wilson operators. So in particular, thinking about the Higgs branch as a Coulomb branch gives us access to a new and interesting collection of coherent sheaves, which we couldn't really access before. And for mathematicians, maybe that's actually a pretty important takeaway, that this Coulomb perspective gives us a new and interesting way of coming up with objects in these categories. Okay, so I had said I want to find mathematically recognizable objects. So sort of pieces of this that as mathematicians we can deal with. And certainly one really good example of a mathematically recognizable object is a resolution of singularities. I had mentioned this with the nil cone, that you have this Springer resolution. And these resolutions also have a natural interpretation in terms of physics. They arise when we turn on real mass or Fi parameters. And again, I color-coded these so I wouldn't get confused. You turn on the mass parameters if you want to resolve the Coulomb branch, and Fi parameters if you want to resolve the Higgs branch. And in particular, in this two-dimensional discussion, I was talking about sigma models, and I really want sigma models into resolutions where I've turned on the real mass or Fi parameters. So for the Higgs branch, again, that's something very natural. That's using what's called geometric invariant theory, or if you prefer hyperkähler quotients, just doing a hyperkähler quotient where the real moment map has some interesting value. So this Fi parameter is a value of the real moment map. For the Coulomb branch, you have to do something a bit weirder, though now, again, in this BFN picture, it's something reasonably natural. You extend your gauge group by adding in a flavor torus, and you can compute the Coulomb branch corresponding to that bigger enlarged gauge group. And that has a Hamiltonian action of the dual of the flavor torus. And you can use GIT theory there. So these are these resolutions described by BFN in this paper, line bundles on Coulomb branches. So there is a natural way of trying to come up with resolutions of Coulomb branches. I should note this doesn't always work. So one of the reasons that I liked restricting to the case of either being abelian or being cyclic quiver gauge theory with a dominant weight is those are cases where you actually will get resolutions out of this construction. All right. So the coherent sheaves on these resolutions we can write as quotients of the category of line operators. So if you are a mathematician, what you're interested in is coherent sheaves, then this is actually a very interesting story because you're getting some new and funny way of thinking about coherent sheaves. But if you're a physicist, well, coherent sheaves are kind of picking out some piece of this bigger category of line operators, giving you kind of interesting structure where you can decompose the line operators into the ones that survive as coherent sheaves and the ones that get killed. So again, for the Higgs branch, this is pretty simple, right? We're doing GIT theory. So we're taking this cotangent bundle and removing the unstable locus from it. So we're quotienting out by all the sheaves that are supported on the unstable locus and all the ones that die when you pass down to this variety. So there are also line operators that kind of were already dead by the time you got to this variety. I should say maybe this guy is exactly sort of the piece of the category of the line operators. Oh God, I think someone's trying to call me. Is everyone else hearing that? I do not know how to stop this right now. Go out.
We can't hear it.
Oh, there it is. There it is. Sorry about that. All right. Are there any questions? Since we paused for a moment there.
Yes, there is a question. The question is it that the procedure doesn't work because the Coulomb branches may not have resolutions, or the procedure doesn't always produce resolutions even when they exist?
Both, actually. So there are Coulomb branches which provably do not have resolutions, and there are also Coulomb branches which we know have resolutions, and this process doesn't work. Though those are a bit less well understood because they involve, maybe I shouldn't totally confidently say that. I mean, there sort of should be examples of that coming up because you should be able to construct orthogonal and symplectic nil cones as Coulomb branches. So I won't absolutely swear to that one. There are lots and lots of examples of Coulomb branches that don't have resolutions. It's sort of very easy to cook those up. In particular, you can get affine Grossmanian slices, which we've proven don't have resolutions, but I think sort of much more than that. You should think that like having a resolution this way is a really weird thing to happen. You shouldn't expect it in most cases. All right. Anything else?
That's it.
Okay. So this variety, this resolution of the Coulomb branch depends on a choice of flavor, right? I said you did a GIT quotient by the dual of the flavor torus. So a co-character into flavor gives you character of the dual, and so that gives you a GIT reduction. And there's a sort of more geometric way to think about this quotient, which is that, well, this co-character gives me an automorphism of the loop space given by applying it to T. So, I mean, if you're thinking about like actual matrices with values in polynomials, this is really like you take your co-character and you put the parameter T in as the value in the map. And basically what you should do is apply this automorphism, very high negative powers of this automorphism, to the identity object and look at the things that are killed by that have no maps of that into them. And that's the stuff that doesn't survive in coherent sheaves on here. So again, if you were interested in these resolutions and you wanted to understand the category of coherent sheaves on them, these include things like T star of the type A flag variety, the Hilbert scheme of C2, then you might be able to profitably study these categories of coherent sheaves by thinking about them as quotients of the category of line operators. And I'll just mention, I'm secretly also telling you what the resolutions are. This is really kind of secretly describing GIT theory categorically, because you can find powers of a line bundle and use those to get a projective coordinate. Okay, in both cases, I have to make choices. I have to choose a flavor, or on the Higgs side, I had to choose a character of my group in order to get a resolution. And I can get different ones which are genuinely not isomorphic as varieties. For example, examples of these are very easy to cook up in the toric case, or actually also in the quiver variety case. And there's an old and very interesting conjecture in algebraic geometry that if you have two crepant resolutions, and symplectic resolutions are always crepant, symplectic resolution is basically a crepant resolution of a Poisson thing, then of the same variety, then their categories of coherent sheaves should be derived equivalent. They won't be equivalent. You can reconstruct the variety from the category of coherent sheaves as an abelian category, but they'll be equivalent as derived categories. And Kaledin actually proved this for most pairs of symplectic resolutions. You need a few hypotheses, but it's not a huge deal. And the way he proved this was constructing an intermediate category, which is representations of a non-commutative algebra. Jeez, okay, sorry about that. So he wanted to prove that these two categories of coherent sheaves were equivalent, and he did this by building a bridge between them, which is this non-commutative algebra in the middle. This non-commutative algebra is what's called a non-commutative crepant resolution of singularities. So there is a fancy definition of that. The point is it's a non-commutative algebra whose representations behave like the coherent sheaves on a resolution of singularities. I think that's all I want to say about that. And when you have such equivalences, of course, you get a very special object on both sides by looking at the algebra A itself as a module over the algebra and looking at where that goes in the coherent sheaves. These give you sort of special vector bundles that are called tilting generators. And so one of the things I was able to do recently by exploiting all of this work of BFN and thinking about line operators was to give a physics interpretation of this work of Kaledin. And the idea is pretty simple. It gets a little harder if you sort of drill down too much. But you want to look at a copy of the cyclic group of order P, which is acting by loop rotation twisted by a flavor. So here I'm taking S to be a pth root of unity, and those act on Laurent series by, well, I act by my flavor, thinking of this as an element. This is in the representation V adjoining T, and also by multiplying the parameter T. So if I want to get fixed points of this, I need to have pth powers of T, because of course those won't be changed by multiplying T by a pth root of unity. And I also have to multiply by T to the minus lambda to cancel out this action. If I look at those fixed points, they're actually isomorphic back to my original space of Laurent polynomials by taking the pth root of my parameter T. And this guy has an action of the loop group with my parameter raised to the pth power, and this map is going to intertwine that with the usual action of G. So what we can do is we can define a vortex line operator in this slightly crazy way by taking the associated bundle for Laurent series, not Laurent series, Taylor series here on the affine Grossmannian, looking at its fixed points under this action of the cyclic group of order P. That maps down here to the fixed points in the loop space, and via this Frobenius isomorphism back to my original space of Laurent polynomials. And then I can take this whole picture and divide out by the loop group. So this guy in the middle, this becomes the Taylor series of V mod the Taylor series of G when I mod out by the loop group. But I'm not totally confident talking about the fixed points of that cyclic group of order P on the quotient. So I prefer to kind of get rid of keep the loop action in place instead. So that gives me a push forward map, and that gives me a D module on here. And it's equivariant for the loop group because of this thing about the actions intertwining. And I should just note that this is a big sum of things of this form of vortex line operators I mentioned before. It always comes from a subspace mod of parahoric mapping to this loop space. It's a big union of such things, and this taking P fixed points, just kind of a convenient way of packaging up that information. It looks, I can just tell you this list of subspaces and parahorics I want, but it looks very unmotivated if I do that. So the combinatorics can get a little complicated, but at the end of the day, it's not so bad. And I'll just note here, we chose a quantization parameter, lambda. This is I should say the flavor, lambda. And I'm also choosing a flavor that gives me a symplectic resolution. These were actually chosen independently. So if I look at this line operator, I get m lambda. That gives me Kaledin's non-commutative Crepin resolution of singularities. And the equivalence Kaledin wanted was taking the subcategory of line operators generated by this guy m lambda and then quotienting it down to the two singularities. So maybe I'll go back here for a moment. I'm saying you can interpret what Kaledin was doing is saying up here, there's this category CA, and it has this guy as quotient and this guy as quotient. And I include this guy as a sub and do the two quotients. And that gives me the equivalences. All right, so yeah, let me just finish up. There are a lot of interesting things you can do with this that I have not had time to get to here, which again are even kind of more mathematical. In particular, this algebra A actually has a very explicit description. It's not just some weird thing. For quiver varieties, you can present it as sort of a KLR algebra on a cylinder. So this kind of unified the two great interests of my life, KLR algebras and these symplectic singularities. Secretly, the symplectic singularities were KLR algebras. You can get explicit presentations of wall crossing functors. So one thing I sort of didn't say here, but I can go back a moment because I still have 2 minutes left. The subcategory I put in here depended on a choice of lambda. And for different lambdas, I get different equivalences between these two categories of coherent sheaves. And when you put those all together, you actually get an action of some generalization of an affine braid group. And again, well, just as I have explicit presentations of the endomorphism algebras, I have explicit presentations of the bimodules that correspond to these wall crossing functors, can construct what's called a Schober. It's a categorical version of a local system. You can verify this Bezrukavnikov and Kaledin conjecture relating the quantum cohomology or the quantum connection and this geometric braid group action by hand in some sense. You can get stability conditions on these categories of coherent sheaves. One thing that I think is actually quite interesting but hasn't really been exploited much is there are also K-theoretic Coulomb branches where Kaledin's tricks won't work. Kaledin won't construct you a tilting generator on those guys. But if you just look at the line operators that gave you a tilting generator in the rational case and use those in the K-theoretic case, they do give you a tilting generator. And we actually use this trick in work with Ben Gamage and Michael McBreen on mirror symmetry for multiplicative hypertoric varieties, which are the K-theoretic Coulomb branches in the abelian case. All right, thanks, and I hope to see more questions.
All right, let's thank Ben for a wonderful talk. So if you have questions, please raise your hand and I will unmute you and call on you. Yes, Greg.
Is it possible to interpret any of your story in terms of singular monopoles?
That's a really good question. I'm probably going to mostly, I think the answer is I don't know. So there's sort of a lot of this physics stuff where it's like, yeah, I would like to understand that too. I'm afraid I don't have anything intelligent to say about it.
Okay. Aswin?
Yeah, hi. Am I audible?
Yeah.
Yeah.
Yeah, so my question is, so from a purely mathematical perspective, is there any uniqueness expected in symplectic duality? Like in the sense that if you have a symplectic variety that has a resolution, is it expected that there's a unique symplectic dual, or can there be more than one?
I mean, the thing I would say is mathematically, we don't know what to expect, right? Sort of all of the kind of interesting predictions have come out of physics. You know, so one thing that's certainly been a big concern for us is you can sometimes write the same variety as a hyperkähler quotient of two different representations and groups. So if you're just looking at, you know, sort of the geometry of the Higgs branch as a variety, you can have, you know, different gauge theories that sort of look the same, and they have totally different Coulomb branches. And we kind of haven't totally sorted out how to resolve that issue. So, I mean, I think the answer is we're not totally sure. Probably you need to remember some kind of extra information, right? So part of what's happening here is there are kind of other things, right? There's this bigger category of line operators, which doesn't survive if you just go to the hyperkähler quotient. And these cases where you get the same hyperkähler quotient, it certainly doesn't look like you have the same category of line operators. So maybe kind of an interesting question would be, can you, you know, what can you reconstruct just from knowing the category of line operators? Because, you know, somehow if you can do that, then there is some kind of uniqueness, right? There's a sort of unique thing that happens with the category of line operators. The A and B twist categories swap places.
Thank you.
Andy has a question.
Hi. When you talk about these categories of line operators, what kind of categories are there? Like what adjectives go in front of the word category?
Oh, yeah. So I've been told to stop saying they're monoidal because they're apparently factorization categories, right? So, I mean, somehow, I mean, probably you know as much as I do about this, right? It's whatever structure you would expect from having lines in 3D, right? So lines in 3D, you can kind of bring them together like this. That's the factorization structure. You can also kind of braid them, but I think that's all kind of bound up in the factorization structure. But usually I depend on like Sasha or Kevin to correct me. When
but so, I mean, do you know the category, you were describing the categories in a pretty explicit way. In that realization of the category, is it known to have this kind of factorization structure?
Yeah, I mean, I think at least for the D modules, that's kind of obvious because, you know, basically like you look at instead of, you know, like, right, somehow it's defined geometrically in terms of a disk. So you like let the disks collide with each other. And So I think that part is on some level kind of obvious. I'm less sure about the kind of coherent sheaf side. But I mean, I suspect people who are very serious about this derived algebraic geometry stuff would kind of look at these descriptions in terms of mapping spaces and say kind of, okay, pair of pants, you're done.
Okay. Thanks.
Mm-hmm.
There was a question, maybe more of a request in the chat, whether you could say something more about tota phase that you mentioned.
Oh, sure. Where was that example? Right. So, yeah, I mean, I guess I'll just say like it is a proven fact that, so if I look at 0G, let me actually make a new page. So if I look at this Higgs branch for 0G, not Higgs branch, Coulomb branch, then the functions on that are just the equivariant homology of the affine Grassmannian. So if you look at this BFN description, they say when you throw in, you know, the sort of interesting thing in the BFN description is when you throw in matter, how does that introduce quantum corrections? But the kind of base case is if you put in the pure theory, then you're just getting the homology of the affine Grassmannian. And it's been known for quite a while now due to work of Bezrukavnikov, Mirkovich, and I might be leaving, probably Bezrukavnikov, Finkelberg, and Mirkovich, that this is the same as functions on the tota phase space. So inside here, there's a copy of the G equivariant cohomology of a point, and those are the tota Hamiltonians. So, I mean, one of the things that I didn't quite have time to say here is, you know, what always happens in this Coulomb branch is there's a copy of the equivariant cohomology of the gauge group at a point, which is the invariant functions on the Lie algebra that shows up in the vector multiplet. And this always gives you an integrable system. So in these cases where you're getting recognizable things, you're not only getting interesting non-commutative algebras, but you're getting them with an attached integrable system. So for example, oh no, not here, yeah, here. I didn't include tota and the total Hamiltonians on this page, but here, when you, for example, get U of SLN, you get what's called the Gelfand-Cetlin subalgebra inside it as the cohomology of a point for the gauge group. So you see, you always keep getting these interesting integrable systems where tota is actually kind of the base example of it, and all the other ones are somehow like quantum corrections of tota.
Does getting the integrable system depend on writing your three-dimensional theory as a dimensional reduction of a four-dimensional theory?
I mean, it depends on writing it as a gauge theory. And I feel like I've heard conflicting things about whether all those gauge theories make sense in the four-dimensional world.
Actually, may I comment on this? This is Samson.
Yeah.
As Nekrasov and I showed, actually, coming from 4-dimension, 3-dimension to 2 dimensions, 4 or 3 dimensions, you get different theories. For example, If you come from 3 dimensions, you can get XXZ model, which is integrable system, or other spin chain. You come from 4 dimension, you get XYZ model. You always get some integrable system, but they're different.
Mm-hmm.
And they can be classified, actually. All this list on which is here on the page can be classified from which theory you start. Only most important thing that this theory has to have mass cap. You're not allowed to have vacuum with 0 energy as in continuous spectrum. So everything has to be with mass. Did I answer the question about dimensions?
I think so. Thanks. So Jan Soibelman has a question.
Yeah, hi Ben. I have a small question to the beginning of your talk. These categories O, which you mentioned briefly, are they described sort of explicitly in terms of these Coulomb and Higgs branches or their symplectic resolutions?
I mean, so right there's sort of the moral answer to this, and then there are a few technical issues about that. You know, there's definition of category O, as in, you know, my papers with Braden, Proudfoot, and Licata, which is, you know, you take this deformation and you look at modules over the deformation that are bounded above in the right way. And then, you know, you can use, so, you know, somehow as a mathematician, I would say the kind of interesting thing is like, for Coulomb branch, right, you get these algebras and they're written in this kind of strange presentation, but somehow the strange presentation exactly allows you to do a really easy analysis of their category O's and sort of give a combinatorial description of the category O's in an easy way. So somehow what's going on in the proof that I mentioned here is basically exactly sort of exploiting this BFN presentation of the Coulomb branch to give it sort of purely combinatorial description of category O. And I'm on the other side using a geometric description, using the sort of Chris Ginsburg stuff and seeing that those kind of match up. So let's see if I can. So, you know, there's sort of basically a story here where you take this variety and you apply localization for a C star action. And there's sort of a clever way you can interpret being a weight module as having to do with localizing for a C star action that has a non-trivial component along the loop. And so you break down to all these finite dimensional varieties, and they're like exactly the ones that describe the category O on the Higgs branch geometrically as push forward D modules.
And for BFN, this description of the category O, kind of, if you start with abstract, it's more or less what you're saying now, yeah. But okay, good. All right, thank you.
And there's sort of this old work of Drozd, Futorny, and Ovsienko, which was about how to take a non-commutative algebra with a big commutative subalgebra and analyze the modules where that big commutative subalgebra acts locally finitely. And it turns out that like this has a like very simple geometric interpretation in terms of BFN. And so like they have some category that in general would be very hard to compute that kind of controls these locally finite modules. And for these Coulomb branch algebras, it's relatively simple to figure out what it is and sort of classify the simples and describe everything in terms of finite dimensional algebras.
Are there any more questions?
I have a quick comment in relation to Andrew's question, but I couldn't raise my hand. I think I'm not sure the co-hosts are allowed to raise hands.
Go ahead.
So about line operators. So the way the line operators in the H-twist are presented algebraically does make it look like a factorization category because one is using the complex structure of the plane transverse to the lines. That's where all these loops are coming in. But the A-twist is topological, and so at the end of the day, that should actually be a braided monoidal category. It's presented in a way that makes that the topological nature of this plane sort of obscure. And it's much clearer on the B side, where Rosansky and Witten and Kapustin, Rosansky, Salina studied these categories for sigma models and actually explained what the braided monoidal structure was.
Okay, there's a question from Davide Gaiotto.
Hi. So at some point, I remember that the characteristic P in math was used to get tilting bundles, right?
Mm-hmm.
In this discussion, there was no characteristic P.
No,
Or did I just
you
make
don't. Somehow it's replaced by this looking at the P torsion inside U1.
Mm-hmm.
And so, like to actually prove that what you're doing is the same as Kaledin's story, you have to go into the characteristic P world, see what happens. And, the point is, so somehow you go in the characteristic P world, you see what happens. You see that the right thing to do is to take the fixed points of this P torsion. And then there's a step in Kaledin's proof where he says, okay, you construct this crazy characteristic P thing. Now find something in characteristic 0 that gets you this characteristic P thing when you mod out mod P. And, I described it in characteristic P as these line operators using characteristic P homology instead of homology over C. And then you say, oh, well, I want something that reduces to this. Oh, I better take the homology of exactly the same thing, but now with coefficients in C.
So do you think there is an actual orbifold in space-time, meaning that the geometry somehow is C mod Z P?
No, I don't think so. I really think this characteristic P thing it was just kind of luck that was how you could kind of get your hands on these vector bundles, right? That, somehow if you're thinking on the Higgs side, it's totally non-obvious what you could do to construct these guys, right? Like the Procesi bundle is genuinely very hard to construct. And it's like the most obvious thing you could do on the vortex side, on the A side. And so I think this characteristic P thing was just kind of a coincidence that gave you access to these vortex line bundles. So I don't think you should think of them as a fundamentally characteristic P thing. You should think of that as just kind of, that was a way of getting your hands on them.
No, I mean the definition that you use with the fixed points. Does it have a geometric interpretation?
I mean, you can you're thinking, that's a good question. Again, I don't know. Right. I mean, somehow I could say, like, think about this list of vortex line operators, but then you would be like, well, that's a weird list. Where did you come up with that? Right. So, I don't know, like, right. Somehow the P, it's not very intrinsic, right? There's this whole picture where, you don't really care about which P you're using. You just use some P and make sure it's big enough. And you can see sort of explicitly in this construction, as once P is big enough, the set of line operators that show up doesn't change. It's just how many times each one of them shows up changes. So somehow, like, there's a collection of line operators that show up that's independent of P, and then choosing P is just like choosing how many times they're going to appear.
When you're doing this analysis with the P, with P torsion, are you somehow in the omega deformed setup or not? Meaning, are these line, are the line defects this? I don't know how to say it properly, but
I'm sorry, I feel like I didn't quite understand a key word you said there. It's a what setup? Deformed setup?
Omega deformed. I mean, I'm not asking the question properly, but
yes. You do this omega deformation, turn on the U1 equivariance in cohomology with characteristic P coefficients, right? And exactly what's happening is because you're taking cohomology with characteristic P coefficients, localization doesn't work anymore. You can't pass to fixed points of the full U1, but you can pass to fixed points of the P torsion, and localization will still work in the usual way.
So you're working characteristic P. Sorry, I keep getting about this.
As I say, like somehow right, I could do this whole talk without saying anything about characteristic P and make true statements at the moment. But, right, if I go to this, statement about like that the thing I'm constructing is Kaledin's functor. Well, Kaledin's functor was constructed using characteristic P. So if I'm going to prove that something is the same as Kaledin's functor, I have to start thinking about how it shows up in characteristic P.
Sure, but if I didn't care about proving that it's Kaledin functor, but only that it's a functor that works,
then there would be no reason to think. At the moment, like somehow proving that it works, I think I kind of prove it by comparison with Kaledin. But, somehow like, well, I was too lazy to give a totally separate proof when I could just compare with what Kaledin was doing.
Okay, so I think we have time for one more quick question.
Yeah.
Jan, go ahead.
Yeah, okay. Sorry. It's I forgot to ask, you mentioned this K-theoretical Coulomb branch sort of interesting. Yeah, okay. What about elliptic?
It's a good question. Yeah, probably. I don't know. I think I briefly got excited about thinking about elliptic Coulomb branches, and I think then I discovered that some group of people had kind of already done the stuff that I would be able to figure out about them, and I kind of lost interest. But like, right, if you presumably you could do this on the elliptic Coulomb branch and get some interesting vector bundle on that elliptic Coulomb branch. And, probably it would be some kind of relative tilting generator over, like the correct symmetric power of the elliptic curve you're mapping down to or something.
And what, instead of you will have what, torsion points on the elliptic curve instead of your
No. It's right. What I would, it's exactly this thing I was talking about with Davide, that somehow like out of this characteristic P stuff, you just get a list of line operators, and then you say that line operator I can interpret as a coherent sheaf on the K-theoretic Coulomb branch, presumably also on the elliptic one. I haven't thought about it carefully, and then sort of locally over the integrable system, if you look at some small open, not a small, but, if you look at a formal neighborhood of a point in the elliptic integrable system, which is now over some kind of symmetric power of your elliptic curve, then on each open, in a formal neighborhood of every point there, you're just going to look like the rational Coulomb branch mapping down to the integrable system at a point with like the same stabilizer in the Weil group. And so like if you had a tilting bundle on that in the rational case before, you get a relative one in the elliptic case.
Okay. And this story with stable envelopes, how it fits with?
It's a good question. This is one of these things that's like on my list to understand someday. I certainly hope there's kind of an interesting understanding of some way of interpreting stable envelopes in terms of this algebra A.
Then that's that's in the holomorphic topological twist. That's the thing that sits halfway between A and B.
The stable envelopes?
That is the twist that's relevant for. So, sorry, I assume the question was about things
Yeah,
that
yeah,
Akinagich
yeah.
and Okounkov had
Yeah.
written about, and elliptic cohomology of stable envelopes and things like that.
So it's not one of these two twists. Yeah.
So the Akinagich Okounkov story is not. It's a twist that's sitting in the middle.
Okay.
That's not fully topological.
Okay.
Okay. All right.
All
Thank
right.
you.
So let me remind you that the website for this series has videos of all the lectures as well as slides. And next week, we're going to have Marco Gualtieri from the University of Toronto. And so let's thank Ben again.